In this video, we're going to look at application of Fourier series. Um, Specifically, we want to kind of review what Fourier series is. And I will use continuous time for this example, but everything I'm going to talk about in continuous time will also apply to discrete time. So if you recall, when I have a function x of t, that function is we'll come up with one that would be in a time domain. So I'm looking at it over time. Now, if I were to take a Fourier series of it, so we write an acronym Fourier series of it, I'll end up with a set of coefficients, a of k's. Okay, and we know the relationship between a of k in the continuous time would be integral going over a period, and x of t times e to the j k, omega 0 being the fundamental frequency, t dt. So and what we're basically saying is, if I've got, let's say, a periodic signal of some sort here in the time domain, when I go over here, I've got a discrete signal which I may or may not have a non-zero value at DC 0. This x-axis is omega, while this x-axis was t, and then I'll have may or may not have some values, some components at first harmonic omega 0, second harmonic, and same on the minus side of things, second harmonic, and on and on. And again, I don't draw it, but this keeps going. So this is kind of what we've been learning and talking about in the previous videos. Now what I want to do is say, okay, how do we use this? Well, we use this by, sometimes it's useful to look at signals over time, but a lot of times it's useful to look at individual frequencies. For example, when you are listening to your phone, the reason your phone doesn't get mixed up, your message that is coming to your phone doesn't get messed up with the Wi-Fi, doesn't get messed up with the TV or radio and all that, is because your signal is being filtered. So we could build a filter like we've learned with with capacitors or inductors or resistors or whatever else we have, but if we are able to translate our signals into a Fourier series or something equivalent to that, we can simply eliminate all the coefficients except for the frequency we are interested in, and therefore we are filtering it. So let's take an actual example so we can kind of put that in practice and see how that works. Let's say someone gives us a signal, and the signal, this is the x of t. The x of t they give us is a square wave, periodic. And this is the x-axis. And let's say magnitude of these pulses are 2. And let's say, just to make things simple, so this, let's say, goes from 0 to, I don't know, 10 millisecond. And let's say this is 50 millisecond. So let's say that's the pulse, and it repeats itself on and on. And they say, okay, what happens? So this is my x of t signal, and the question we're trying to find out is what happens if I take my x of t and run it through a filter. So I've taken my f of t, and let's say, and this is going to be an h of t in a sense, and my h of t is just a filter actually this would be probably h of s transfer function, and this is omega, and this is 0, and let's say this is a low pass filter. So I'm to get a transfer function for my low pass filter, and it looks like this, and again this is 0, and it pops up here. Let's say this is even 1, and let's say the cutoff frequency for this filter is sitting at, let's say, 150 radian per second, 150 pi to minus 150 pi. And let's see and then the question is, if I were to take my x of t and run it through this HFS, this low pass filter represented by the signal here, what would I get back out as y of t? So that's the main question. So let's work through this thing and see if we can get there. So if I were to look at this signal, what can I derive from here? So first thing I got to do is I got to say, okay, this thing, the period is going to be from 0 to 50. So period is 50 times 10 to the minus 3 seconds, which in turn tells me omega 0, which is 2 pi over t, will be, if we clean this up, will be basically 2 times 10 to the 3 pi divided by 50. Okay, so in another way of writing this is going to be 40 pi. Great. So omega is 40 pi. Well, it would be really nice if I could find out the Fourier coefficient of the signal. Now, if you recall, we know that the Fourier series coefficient for this thing, a of k, is basically an integral over a period of t of x of t e to the minus jk omega 0 t dt. All right. So all I have to do is basically plug in what I know, a of k. The period might as well go from 0 to 50 millisecond. So would be 50 milliseconds is 5 over 100. And then x of t, I don't know what x of t is because x of t changes, goes up to 2, and at 10 millisecond drops down, so I don't know what that is, or I have to break this out to 2 pieces if I'm going to do this. Then e to the minus j k omega 0 t dt. Okay, and that also omega 0, I know what that is because I just calculated up there is 40 pi. Great. So I know that this x of t is only non-zero from 0 to 10. So one way of fixing this is I write a of k is equal to integral of 0. So it would be 1 over 100 2 e to the minus j 40 pi k t. That's great, dt. Okay. Oh, I forgot something. Here there's a 1 over t that needs to be added here, and t is 50, so it would be 1 over t would be basically 10 to the 3 divided by 50, or 20. So I'm going to have to put a 20 back here to count for 1 over t that I forgot to put in there. All right. So so this will be basically 40 e, and then I gotta integrate e, and hopefully by now we all know how to do that. It's gonna be basically the power comes down on the bottom, so it will be minus j 40 pi k e to the minus j 40 pi k t. And the integration would be from 0 to 1 over 100. So all we have to do is just do a little bit of work to clean this up, and we'll end up with, so I kind of jumped a little bit. So I took this integration that was here and I cleaned it up. The first time we put the 1 over 100 in here, and you'll end up with minus j 4 over 100 pi k and j over pi k. And what I did, I took the minus j to the numerator. We can't do that. I multiplied the top and the bottom by j. And then for 0, this e to the 0 is going to be 1, and what you're left is just the coefficient. So that's what we got. So what is, let's go ahead and draw this thing. So let's see, hang on.